My name is Daniel Sunday Okoliko, a first year student at Nazarbayev University from the Department of Physics. Now, have you imagined a world where we could harness sunlight not just to power our homes, but also to clean polluted water and drive chemical reactions that produce green energy? The key to this future lies in efficient photocatalytic materials that can use sunlight to trigger useful chemical processes. One of the most promising absorbs visible light, it is stable and environmentally friendly. Yet, despite its promise, bismuth vanadate still underperforms, mainly due to poor crystallinity, low charge mobility, and high recombination of photo-generated carriers. My research aims to solve these problems. The research gap and my contribution. Now, previous studies mostly focused on bismuth vanadate powders made by chemical or hydrothermal routes, which lack control and scalability. However, very little is known about how magnetron sputtering parameters such as power, deposition time, and annealing temperature affect bismuth vanadate structure and performance, especially when combined with high current ion beam irradiation. My contribution is developing a systematic understanding of how to engineer bismuth vanadate thin films with controlled crystallinity, morphology, and band structure, optimizing them for solar-driven photocatalysis. Now, the method. I deposited bismuth vanadate thin films using direct current magnetron sputtering, varying key parameters such as power. Now, the power was varied between 50 to 150 watts. The deposition time was between 30 to 90 minutes, and the annealing temperature was from 300 to 600 degrees centigrade. Afterward, the films were exposed to argon ion beam at high currents and controlled energy. This irradiation introduced defects and lattice strain, which I hypothesized and fine-tuned the film's electronic structure. Now, to characterize these changes, I used advanced techniques including X-ray diffraction (SRD), scanning and electron spectroscopy (SEM), as well as atomic force microscopy. Now, the result and the interpretation. Increasing sputtering power to 100 watt improved crystallinity and reduced the optical band gap to about 2.42 electron volt, enhancing visible light absorption. It was also discovered that extending deposition time to 90 minutes produced smoother, denser films. Why does this research matter? This study provides a blueprint for turning functional oxide like bismuth vanadate. It is a step forward to more efficient solar-driven photocatalytic system. These findings could directly influence clean energy generation, and pollutant degradation, as well as hydrogen fuel production. The key takeaways are this research shows how precise control of magneton sputtering with ion beam irradiation can engineer and transform ordinary material into one with extraordinary potential, helping bridge the gap between laboratory discovery and real world sustainable technology. Thank you.